Welcome to the chapter on ketones and aldehydes. We've already been talking about ketones and aldehydes. We've done a few reactions of ketones and aldehydes with the Grignard, and we've also talked about how to synthesize ketones and aldehydes through oxidation reactions. So we're going to talk about the carbonyl compounds. And a carbonyl compound has a carbonyl group. I will review a little bit about the IR and the mass spec. I will review the functional groups that contain carbonyl compounds. We'll talk about how to synthesize the ketones and aldehydes. And we'll talk about those reactions. A lot of them will be review, but you'll be it'd be very important to understand these. You'll see these in your exam. And then we will talk about the reactions, the different reactions of ketones and aldehydes. And of these reactions, you are required to know two reaction mechanisms. And so I will give you the two reaction mechanisms for these reactions that you will be asked for your open response. So let's look at functional groups. So if we have, this is acetone, that is a ketone, because you have your carbonyl, and then you have two carbons on that carbonyl. So when you have a carbonyl, you have to figure out what is on one side of the carbonyl. Okay, so if you have your carbonyl here, and then you always are going to probably have a carbon there. Then what if you have a hydrogen here? This is going to be an aldehyde. If you have this, so you find your carbonyl, and here's your carbon, and then what do you have here? You have an OH. So this is a carboxylic acid. Here you have a carbonyl. You have your carbon over here, and then if you have an oxygen and then another carbon on that side, then you have an ester. If you have your carbonyl here, your carbon, and you have a Cl, that is an acid chloride. And then the other carbonyl compound that you could have, something like this, where you might have a nitrogen. So here you have a carbonyl, you have the carbon over here, and then what do you have? You have a nitrogen with, nitrogen has 3 bonds, so it can also have hydrogens and carbons, but this is called an amide. Some people call it an amide or an amide. Now, what we're going to be talking about today, we're going to be talking about the ketone and the aldehyde. And we'll be doing different functional groups that you can interchange from one to the other. So looking at the ketone and aldehyde, its structure, this carbon here is an sp2 carbon because it's connected to 1, 2, 3 things. And remember, if you add your 2 plus your 1 equals 3. So it's sp2, and we know sp2 is flat, so this is flat, and or we could say it's trigonal because it's 3 things, 1, 2, 3. Planar. Planar means it's fat. And between this oxygen and carbon, you have 120 degrees. Between these two carbons, you have 120 degrees. Between the oxygen and carbon here, you have 120 degrees. So it's sp2 hybridized, and the carbonyl bond is going to be shorter and stronger, more polar than the alkenes. So we've talked about alkenes. So we've seen this double bond here. This is an alkene. And double bonds are going to be shorter and stronger, short and strong, than a single bond. Okay, single bond. But if you put an oxygen in there, so now you have polarity, because this is more electronegative. So now you have polarity difference here, making this carbon more positive. You can show your dipole like this, and this is going to be even shorter and stronger than a carbon-carbon double bond. So this one's going to even be shorter and stronger than the alkene. Now, resonance. You do have resonance structures for an aldehyde and ketone, so let's be able to draw those. So these electrons here, the pi bond, can go up to form, so we can go from a pi to a lone pair. That makes this positive and this negative. This oxygen here is still an sp2 hybridization because it participates in hybridization resonance. Now this is your major, so if you apply, and this is going to be your minor. Major resonance structures have no formal charges. So, but what's interesting about your minor, when you're figuring out reaction mechanisms, so if you go on to take organic 3 and graduate level organic, you decide you want to do drug design, you'll learn that it's usually this second minor resonance structure that actually is the dominant intermediate species in reaction mechanisms. Okay, so we have the dipole moment there. We have a pretty strong dipole moment. So what are we looking at here? We're looking at, for a ketone or something, about 2.9 dBi. So that is it. What do you have in like you all know that this is an alkyl chloride, right? And you've been used to that in your SN2 reactions. What is that dipole difference? That is a 1.9 dBi. Okay, so these are, the carbonyl is a polar bond. You're going to also need to know nomenclature. I don't normally go over nomenclature. I just let you kind of review that. So we can look at it real quick and then you can do more problems. But here you have to include your carbonyl, and you want it to get a lowest priority. So 1, 2, 3, 4 is your longest chain. And you would say 2-butane. We're going to drop the E because it's a ketone, and we're going to add -one. So this is 2-butanone. And 2-butanone is actually the species, the active species that you smell sometimes when you're popping popcorn. Okay, we'll do this one here. Okay, so what is this? You want to find your longest carbon chain, including your carbonyl. So 2, 3, 4, 5. 5 is pentane, right? And you want to give your carbonyl the lowest number, 1, 2, 3, or 1, 2, 3, so it doesn't matter. 1, 2, 3, 4, 5. So now it's 3-pentan, drop the E, add -one. And then we have substituents here. We have a 2 and a 4 dimethyl, dash 3-pentanone. And sometimes people put the 3 in front of the -one. And either way is okay. If you have a cyclic one, so if we have a cyclic ketone, something like this, then your ketone has a higher priority than the double bond, than alkenes. Okay, so that means it gets the lower number. So you'd want to start with that as 1, and then you'd have to go through this one. You'd want to go clockwise so you can get that low priority for the alkene. So this is a cyclohexene. So here you could do 2-ene. and then we want to drop the E, and we would want to add, and you could just add on. You don't have to do one, but you could. To cyclo, hex, 2-ene, you could do one on, or you could just do cyclo, hex, 2-ene on. If you don't have a number for the on, it would be understood 1. So there's your cyclo. Aldehydes, how do you name aldehydes? So if we have an aldehyde here, let's do this. Aldehydes are always going to be at the end, so they're always going to be a 1, so you never have to give them a number. And it gets highest priority, so there's 1, 2, 3, 4, 5. Aldehydes and carboxylic acids, they have to be the 1. So here we have 3 bromo, and 5 is pentane. We're going to drop our E, and we're going to add Al for aldehyde. So 3 bromo, pentan, al. Okay, so if you have a carbonyl as a substituent, so something like this, so we have a ketone and an aldehyde, then the aldehyde has higher priority, 1, 2, 3, 4, 5. This would be a substituent. And so how do you name that substituent? You know, like you do methyls and ethyls. This is going to be an oxo. So this would be 3-oxo, what's 5? Pentan, so 3-oxo, pentan, al. Okay. You should look at your priority list when you're taking your exams. You will need to do a little bit of, on your final exam, you'll have I want to say a few naming. You might have about 5 naming. And so you have to know your priority groups. And in this chapter, it has a list. I'm looking at your slides that are available to you on your Blackboard. Your highest priority is going to be a carboxylic acid, and then esters, then aldehydes. So we're getting up here now, aldehydes and ketones. So that means the highest priority means they get the lowest number when you're figuring out your longest chain and how to name them. Amines are under ketones, and then we have alkenes and alkynes. They're equal there. Below them are ethers and halides. Okay, so this is the highest and this is the lowest priority. Now, you can also look at common names. Let's look at their boiling points and their solubilities, because that lets you know about their physical properties. So when I say boiling points and melting points, you need to think intermolecular forces. So what kind of intermolecular forces do ketones and aldehydes participate in? Well, they have the dipole. So they do dipole-dipole. Of course, they do van der Waals, because van der Waals is lower. Van der Waals are kind of what you see with alkanes and alkenes, with carbon-hydrogen bonds, the hydrocarbons, and these also have hydrocarbons. So if they have van der Waals, they all have van der Waals. But then the highest one, the more dominant force is for aldehydes and ketones, is the dipole-dipole, because of this polarity. They do not do hydrogen bonding. So when you're dealing with melting points and boiling points, they just have dipole-dipole. So if you had a resonance structure here, you could see that this positive and the negative here, then this would orient itself next to another. So the orientation here is going to be with the positive carbon and the negative, electronegative oxygen. And that's going to, and then how do we break open this bond? So this is where we're talking about boiling points and melting points. They're going to have low melting points. The boiling points, let's look at acetone. Boiling point is about 56 degrees. Now, propanol, so equivalent number of carbons, is 49 degrees Celsius. So the aldehyde is going to be more volatile. It's going to be less of a dipole-dipole interaction than you would with the ketone. Compare this with a similar molecular weight structure such as butane and propanol. So butane just has van der Waals, right? And it has 0 degrees Celsius. Okay, so the dipole is worth about what? 50 degrees Celsius. Now, the propanol can do hydrogen bonding. So how would we do hydrogen bonding here? We show it like this. And then this would be hydrogen bonding there. And that is worth 97 degrees Celsius. So that's its boiling point. So you can tack on another 45 degrees for hydrogen bonding. And hydrogen bonding is a more dominant force, as you can see, by about 40 some degrees. And so that lets you know a little bit of your properties. Now let's talk about solubility. When you're talking about solubility, you're asking the question, how does it react with my solvent? How does it interact with my solvent? So in water, you do have a hydrogen in water that can now form a hydrogen bond with water. And so that makes them, some of these carbons, usually it's about less than 5 carbons, are going to be miscible, means soluble in water, because it will form hydrogen bonds with water. All right, IR spectroscopy, we've talked about that a little bit. You're looking for the carbonyl. That carbonyl is going to show up around 1710 reciprocal centimeters for a ketone. For an aldehyde, it's going to be a little bit higher, 1725 reciprocal centimeters. But we also see this CH bond here, and that's going to show up as a 2710 and a 2810 reciprocal centimeters. So that's how you can tell. You see that they have a ketone. So you see that it has the carbonyl. And then if you don't have any other peaks, then you can say it's a ketone. But if it has these little peaks here to the right of that sp3ch that you always see at 2900, those 2 additional stretches, you say, hey, I think I have an aldehyde. If you have conjugation, so if you have a double bond here, you're going to get a decrease. So it will go from 1710 to more like 1685. So you're going to lose about 40 reciprocal centimeters. Now, the other thing you usually get is a Proton Nmr spectra. So here, this CH here, this hydrogen, the Proton Nmr, is usually distinct. You're going to see it at about 9.8 ppm, so between 9 and 10. So that's how you can tell if you have an aldehyde. These carbons, hydrogens here that are alpha, we call this alpha to the ketone. So this is your ketone, this is alpha. Those usually absorb around 2. So you can see anywhere from 2.1 ppm to 2.4 ppm. So they're going to show up around 2. That's the carbon NMR. You're going to see just these regular carbons here showing up around anywhere from 20 to 30 ppm. But you're going to see a carbonyl. That carbonyl will show up around 210, 208 ppm. So just regular alkanes show up around 20 or 30 ppm. The carbonyl will show up around 210. Mass spec. Okay, so mass spec, you usually just have your you can, I wouldn't even really worry about it. You just look for your molecular weight of your entire molecule. All right. These UV, what about UV? Ultraviolet. We do have a little bit of a, it's called a chromophore. Chromophore will show up in UV. And if you have conjugation, you'll have more, because conjugation is worth about 30 nanometers. But the carbonyl is a conjugated system, so it's, you can see a little bit. And you can do remember the HOMO-LUMO transfer. So you do have that. And what the HOMO-LUMO is transferring is this pi electron to a non-pair. All right, so let's talk about ways to make ketones and aldehydes, because that's what we do when we talk about a new functional group. So how do we make ways to synthesize, that's our word, synthesize for make, aldehydes and ketones. So let's see if we can review some of these reactions. One, if you want to make new ones, you can take a Grignard or an organolithium, and you can add that to an aldehyde. So let's take methyl Grignard and let's react it to an aldehyde. So here we have an aldehyde. Here's our delta positive, delta negative. Those electrons here will attack the carbonyl. Those electrons go up. You know, this makes for a tetrahedral intermediate. This is a mechanism you need to know. So here we have this tetrahedral intermediate. Now we can go ahead and add a little bit of acid, because you do the workup when you do your Grignard and your separatory funnel. And here we have an alcohol. And what kind of alcohol do we have? This carbon oxygen is bonded to 2 carbons. So this is a secondary alcohol. And now we can oxidize that. So we can use PCC, pyridinium chlorochromate. That would be my choice. We can also do any kind of chromium, because secondary alcohols will then oxidize. You can put O there in brackets, to a ketone. For oxidation reductions, we don't usually draw electron flow arrows. So it's usually when we just focus on the nucleophile electrophile. So here you have a ketone. And so when you organize your thinking, you need to say, oh, I go from an aldehyde functional group to a ketone. Now, could you have done this with a ketone? Well, if you added this with a ketone, and you had a Grignard, and you react this with a ketone, what are you going to get? What is that? That's a tertiary alcohol. Can tertiary alcohols oxidize further? No. So one way to make ketones is to go from an aldehyde and a Grignard or an organolithium. You can also oxidize primary alcohols. So let's look at that. So you take a primary alcohol and you can add PCC and dichloromethane usually. So remember what PCC was, pyridinium chlorochromate, CrO3, okay, and dichloromethane, and this will take a primary alcohol to an aldehyde, and that's really nice when you can stop an aldehyde. So that's how you can make an aldehyde from a primary alcohol. You could also use a sworn oxidation, which I call the pig oxidation, and that uses DMSO and oxalochloride. Let's see, minus 78 degrees, and triethylamine. Got to have all those reagents. Okay, the other thing, what if you had a secondary alcohol? And you could do the same oxidation, and that would give you a ketone. So oxidation is a way of alcohols, is a way to make ketones and aldehydes. Another way to make ketones and aldehydes is ozonolysis of alkenes. These are all review reactions that you need to be familiar with. If you had something like this, and you add ozone, and then you follow it up with DMS, which is dimethyl sulfide. And dimethyl sulfide becomes DMSO. So this is DMSO. It's a heavy boiling solvent as your product, and it gets one of these oxygens, and two of the oxygens then get delivered to break ozonolysis. It breaks this double bond, so we get a ketone, and then what you don't have here is a hydrogen drawn, and you see that that gives you an aldehyde. So this is what you get in your flask after you react with ozone, and then you break up your ozonide with the DMS. So those are ways to make some aldehydes and ketones. We've also talked about Friedel's Craft, because that's a carbonyl, so we can do aromatic. So let's look at Friedel's Craft. So Friedel Craft reaction. So we can take an acid chloride, and we have to add some Lewis acid, and then we can, let's take toluene. And so if we add this here, then we have to make a strong electrophile, right? So our strong electrophile becomes this psyllium ion, and then we have this is toluene, and that methyl group is an electron donating group, and it's going to be an ortho-para director. So we'll just go with our para. So we draw this. You know, right now I'm going to draw my sigma complex. And we have a hydrogen there, we have a positive there. That's my sigma complex. And I'm not going to draw all my resin structures. I will just show, let's do aluminum Cl4 minus, taking the hydrogen and doing re-aromatization to give us a ketone. So here is a aromatic substituted ketone. So that is how you would make that ketone. Another way you can do is hydrations of alkynes. Hydration of alkynes. This is also review. So if you add mercury sulfate and sulfuric acid, then you get 1, 2, 3, 4, you get a enol, and the OH adds to the more substituted carbon, so that's regiochemistry. And I do my little enol tautomerization here, like that. We can go tautomerization. It's an equilibrium arrow. So enol tautomerization, 1, 2, 3, 4, 1, 2, 3, 4, and there we have a ketone. Now if we react the same alkyne with isoamyl boron, and then we treat this with hydrogen peroxide in a sodium hydroxide solution. Isoamyl boron is isoamyl, 1, 2, 3, 1, 2, it's 5 carbons. Isoamyl boron, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so that is a sterically hindered boron, so we'll just deliver one of the hydrogens. That's why you don't do BH3 for alkynes. And then you would get the enol on the less substituted OH, and then that undergoes enol tautomerization to give you an aldehyde. So this is how you can make aldehydes from alkynes or ketones from alkynes. This is called hydroboration, followed by oxidation of alkynes. The other thing, so this will be a new reaction of how to make ketones and aldehydes. Let's look at 2 reactions. So those were review, so new reactions, and one's from nitriles. So if you have a nitrile and you react this with a Grignard, so let's don't do the R groups. Okay, so here we have a nitrile, and let's do ethyl Grignard. So what you'll see here is this has a polarity. Okay, so carbon is slightly positive, and here we have a strong nucleophile. So our Grignards are strong nucleophiles, so the electrons can go there, and then you get addition of a methyl group, ethyl group here, and then this carbon forms a double bond. Those 2 electrons then we're going to hang out with magnesium. Now, then you can add acid, and you'll hydrolyze this. And this is important because you're going to start learning a new functional group. These are amines. Now, amines are like your carbonyl group. If you add a little bit more acid, this gets protonated, and so the nitrogen gets protonated, and then the water will add, the oxygen will add to this carbonyl, and then that leaves, and we'll look at some mechanisms in which you can hydrolyze the amine a little later. But this makes a ketone. So basically you can take these nitriles, you can add Grignards to them, and then you treat them with acid, and it goes through an amine functional group, which hydrolyzes to a ketone. Now, you can also add lithium aluminum hydride to these nitriles. So let's look at lithium aluminum hydride. So if you take this nitrile here, and this should be linear because it's sp. Okay, so here's your nitrile. If you add lithium aluminum hydride, and you remember that's just adding like a nucleophilic hydrogen, this is going to attack here, and then this is going to go to a double bond. This will form a complex with your aluminum lithium complex. And your hydrogen has been added here. Okay, now you can treat it with acid. It's going to go through an amine, and then it'll go through a ketone. So now we have 1, 2, 3, 4, 1, 2, 3, 4, and this is how we have an aldehyde. Okay, so that's one way to make an aldehyde, but it's really not lithium aluminum hydride because that would be too strong. So we know that lithium aluminum hydride would reduce this all the way down to the alcohol, so don't make that mistake. Okay, so what kind of hydride delivery? It's called Dipole, and sometimes you'll see it as Dipole H. Okay, and you have to do this at minus 78 degrees Celsius. But Dipole is aluminum and diisobutyl. So 1, 2, 3, 4. 1, 2, 3, 4. Diisobutyl aluminum hydride. Okay, and usually you have another H here because that makes that negative, and then lithium. So this is Dipole, but it delivers the hydride, but it only delivers one because it's sterically hindered. And then Dipole, you work it up with a little bit of acid, H3O+, so you would write 1 for the Dipole and then 2 for H3O+, and you would get an aldehyde from a nitrile. So those are two ways to make ketones and aldehydes from nitriles. The other way you can do this is through an acid chloride using Dipole as well. So let's look at, if you had an acid chloride here, and you treated it with 1 Dipole, and then 2, you always have to work it up with a little bit of acid, you would get an aldehyde. So what's special about this is it does deliver the hydride, H- here, as a nucleophile. You get your tetrahedral intermediate. And then this reforms your carbonyl, and the lithium leaves, and you form your aldehyde. Now, we can't use lithium aluminum hydride because lithium aluminum hydride is a strong reducing reagent and will reduce the aldehyde all the way to the primary alcohol. But Dipole will leave it at the aldehyde stage and deliver just a halide. Another way with acid chloride, so this is one way with acid chloride. Let's look at another way with acid chloride. If you take the same acid chloride here and you react it with a thing called a cuprate. A cuprate is, you'll see it R2 copper lithium. Cuprates are really interesting from the standpoint, let's look at something like this. Yes, you have a metal, so it makes this slightly negative because metals are always positive, right? So here you have this cuprate, but it's mild, and copper will do 1 addition. So here you have this addition here. You make your tetrahedral intermediate. You add 1 addition of this ethyl, and then the copper is going to kind of hang out here. You'll just still have an ethyl and lithium. This will reform the carbonyl. Chlorine is a good leaving group. And we make a ketone. Copper is a really nice metal to work with. It's not as strong of a nucleophile, like the Grignard. So if you remember with the Grignard with an acid chloride, you get twice addition, 2 times it adds with a Grignard to give you a tertiary alcohol. So you saw that on your previous exams. So, but here with cuprate and acid chloride, it's only going to add 1 time. So this will stop at a ketone, and that makes a ketone. Okay, so those are ways to make aldehydes and ketones. You do have a lot of review reactions. You do have some new reactions with diabial reagents with acid chloride. You have a new reagent of cuprate with acid chlorides. And then we've talked about the imines. And an imine is a new functional group in which we can add different organometallics to a nitrile. All right, so let's talk about now the reactions of aldehydes and ketones as your starting material. So aldehydes and ketones. So aldehydes are faster. They're more reactive than a ketone. Part of this is because they're more, this is more delta positive because the hydrogen is not as electron donating as carbon, and it's not sterically hindered. So there's no steric hindrance there. I usually think of them as about 10,000 times faster. So what happens if you have an aldehyde and your aldehyde's reacting too fast, you can always tone it down with adding a ketone or vice versa. Sometimes with ketones, you're going to have to heat the reactions. Now, these are your electrophiles. So strong nucleophiles will attack a carbonyl. And this is review. You've seen this. So this will attack a carbonyl, and your mechanism undergoes a tetrahedral intermediate. And with acid workup, we get a tertiary alcohol. So these are reactions you're familiar with. Aldehydes are going to be more reactive. So this is with a Grignard. You could also react this with sodium borohydride. So we know that sodium borohydride is a milder reducing reagent. So reducing reagents, what do? They add hydrogen, right? So you could do, sodium borohydride. If you look at its Lewis structure here, sodium metal, it really adds a hydride. And so what does that look like if we add a hydride? Take those electrons there, add to the carbonyl. This is going to kind of hang out with the sodium and the boron. We add the hydrogen here, and then you're going to have to do a little bit of acid-water workup, and you basically get 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. You get the alcohol, and this is a secondary alcohol. That carbon's bonded to carbon. So from a ketone, we can do a reduction reaction with sodium borohydride to get the secondary alcohol. We've talked about like an aldehyde. We've already done aldehydes give you primary alcohols. Now the new reaction that you need to learn, there's several new reactions that you need to learn. I'm going to say 3, and you need to know the mechanism for the acetal. And then, well, 4 reactions. So we have 4 new reactions in this chapter. So those are review. The Grignard addition and the sodium borohydride addition. So the reaction with strong nucleophiles are new reactions. old reactions. We're going to talk about some new reactions here with mechanisms. So, hydration. So we're going to make hemiacetals and acetals. So you need to know this reaction mechanism. There are about 6 steps, reaction steps. And I want to be able to see that you can draw your electron flow arrows and formal charges. So what happens when you take a ketone and you react it with a little bit of acid, H3O+, and water? Now, the acid a lot of times is going to be PTSOH. What is that? Para-toluene. So toluene, para-toluene sulfonic acid. And this is your acidic proton right here. So this is an organic acid. It's my favorite acid. So that means you can put it in organic solvents and it will deliver this acidic proton. And so step 1, and you need to be able to write these out, is protonation of the carbonyl, oxygen. So that's the first thing that happens. So you need to draw that, these electron flow arrows. And so you don't have to draw out the para-toluene sulfonic acid. You can write H3O+. I mean, it's a generic thing, but it's catalyst. So this is a catalytic amount. So we're going to have to regenerate it. So here we have 1, 2, 3, 4, 5. And we have protonation, makes that a positive. And this is, water is that a strong nucleophile or a weak nucleophile? This is a weak nucleophile. So we've seen how carbonyls react with strong nucleophiles. When you have a weak nucleophile, you have to have your first step of protonation. Okay, so we protonate it. Now we have activated our carbon. So what does that look like? If you did your resonance structure, you would see that we have activated this carbon, our electrophilic carbon. It's very positive now. And so step 2, the nucleophile, the weak nucleophile, which in this case is water, attacks the carbonyl carbon. So here we have water. The water is going to attack this carbon. So you can do the resonance structure, or you can tag it with the carbonyl and the oxygen going up. And what do you get? You get now, we're not there at the intermediates yet. When you get to intermediates, you've got to have neutral. So then step 3, you need to deprotonate the oxygen to give a neutral hemiacetal intermediate. So we're halfway there, folks. Hemiacetal intermediate. So now we got to regenerate our acid. And that will generate H3O+. So we've regenerated our catalyst. And we have made a hemiacetal. And I want you to learn this functional group here. So, and it could be, sometimes you can see in your reading hemiketal, because it came from a ketone, but hemiacetal is widely accepted and it's interchangeable. The reason why this is important, your sugars. You've heard of carbohydrates before? This is carbohydrate chemistry. So it's very important to understand this in biochemistry. So this is a hemiacetal. Now, that means it's halfway there. So now what we have to do is now we have to protonate one of these OH groups water's going to attack again, and we're going to reform our carbonyl to form an acetal. So the next step to form an acetal. So we start with our hemiacetal. So here's our hemiacetal. And so step 4 now, we're going to protonate the OH. So we want to make it a good leaving group. We need a leaving group. So here we have H3O+, which is our acid, and we got to show protonation. Let's protonate the original OH. Not that it matters. Okay, so here we're going to protonate. So we show protonation here. And then we're going to now what I like to do is reform the carbonyl. So step 5, we're going to reform the carbonyl. Now remember, when you reform the carbonyl, this is a driving force. So this is an energetic driving force. So here we're going to reform the carbonyl, and when we do that, H2O leaves. So what does that look like? This kind of turned inside out here. So we reform the carbonyl and water leaves. Now we can have and you don't really see anything here. Step 6 here, you deprotonate the carbonyl. Oxygen to form a neutral. So what you reform your catalyst here, and so it forms neutral. Now, so this looks just like our starting material, doesn't it? And this is what happens when your nucleophile is water, and you have water like acetone. If you have your acetone water, acetone, if you put a little bit of acid in there, then it's actually going to be acetone, and it's going to be equilibrium with the what we call a hemiacetal, or the hemiketal. Okay, so that's a new functional group. Now, where you have a new reaction is what if your nucleophile, and this is a weak nucleophile, is an alcohol. So let's react it with methanol. Now we're going to do the same steps. So we're going to form the hemiacetal first, and then we're going to go to the acetal. And so now our reagents are a little bit of acid and methanol. So let's take this 2-butanone, and we're going to react it with H3O+ and methanol. So step 1, protonate the carbonyl oxygen to activate the carbonyl carbon. So we have this here, and we show our protonation step. And so now we have an activated carbonyl. Now we take methanol, our weak nucleophile. So step 2, our weak nucleophile, and this time it's methanol, attacks the carbonyl, carbon, your electrophile. It goes there, and we have OH, CH3, and we have oxygen, hydrogen. All right, So you see, that's your mechanism there. Now, we're not there yet. So to get there, step 3, our intermediate, we want our hemiacetal. We have to deprotonate the nucleophile, the added nucleophile, to give yourself the neutral hemiacetal. This is not hemiacetal, and we're going to regenerate our acid. So this regenerates our acid, H3O+, and it forms our hemiacetal, our new functional group. Like I said, this is what sugars do. Okay, so there we have a hemiacetal. So you see you have an OH added and an OR added. That's your hemi. Now we want to go on to form the acetal. So let's start with OCH3 and OH. Now step 4 is going to matter. We're going to protonate the OH with your acid to make water a good leaving group. So water is a good leaving group. So we're going to react this with our acid now, and we got to protonate this, step 4. And we're going to show this step. OCH3, let's put our lone pairs in because we're doing reaction mechanisms. OH, here's this. Okay, so now it's ready to be a good leaving group. So step 5, we're going to reform the carbonyl oxygen as water leaves. So these electrons come here, water leaves. Now we have reformed our carbonyl. Okay, so we have our reformed carbonyl, and this is in resonance structures with this. So now we can have step 6. We can have another methanol, which is a weak nucleophile. We'll add to the carbonyl. Carbon. So here we have, we can just do CH3OH, and this is going to add here that carbonyl. And then we have this one here. And so step 7, you need to deprotonate the added nucleophile to give you a neutral final product, acetal. So we're going to regenerate our acid here, H2O, and that gives you H3O+. We regenerated our catalyst, and now we have an acetal. So this is an acetal. So that's kind of a big deal. That's what carbonyl chemistry does. A lot of times this is equilibrium. Notice we're generating, we've got to pull off the water. And so this is all equilibrium arrows. I drew them as irreversible arrows, but it's equilibrium. And so what you do is Le Chatelier's principle. You would use a thing called a Dean-Stark trap. A Dean-Stark trap looks like this, and you can fill it up with toluene and water, and you can distill off the water. And so the water will collect in the bottom here, and that will drive the reaction to completion. So you pull off the water, and that will drive yourself to the acetal formation. So let's look at a cyclic acetal. So these are great for acetals, are great protecting groups. So if you have something like this molecule, okay, so you have this molecule, and you want to make this molecule. All right, so how would you do that? Well, maybe you want to add, what's the change here? We've added an ethyl group, haven't we? And made a tertiary alcohol. How do you do that from a ketone? Could you add a Grignard and then treat it with acid? Work up. Could you do that? Well, if that happens, let's say one equivalence. What would you probably get? You probably would get this, right? And why would you get this? Well, you know that aldehydes are more reactive than ketones. But you can use the acetal as a protecting group. So what you can do, since this won't work, you could add, these are kind of my favorite, the cyclic. This is glycol. This is antifreeze. It's really bad. Okay. Acid, you probably get some para-toluene sulfonic acid. That's a TS. And then you could add your Grignard. So what if you did this sequence? So that's 1, 2. This would be a 3, 4. Okay, what would you get then? Then you would get your product. Okay, so let's look at that mechanism. And you don't have to go through the whole mechanism. I can go through the whole mechanism, but when you're doing these, what I would expect, unless I ask for the mechanism, I would expect you to do whatever your product is for step 1, which would be like, okay, the aldehyde is going to react faster, and this is your product from step 1. There's step 1, and then you have your Grignard from step 2, right? Come here, and then that would give you your tetrahedral intermediate. So this would be from step 3, you would get your, and you know this would be a magnesium bromide, right? And then you would add your ethyl here. Now, the last step here is H3O plus, H3O plus. And so what does that do? Well, if you add H3O plus, you know that quenches that, right? So you get that, but it also removes an acetal, because remember this is an equilibrium. So if it removes your acetal, it reverses the acetal. So here you see that that gives you back the aldehyde, because this is a carbon bonded to 2 oxygens, and here it is bonded to 2 oxygens, and then it also replaces the magnesium with the hydrogen here. And so that's how you can make a tertiary alcohol from a ketone in the presence of an aldehyde. And that is very powerful. So you don't have to do the reverse mechanism of adding acid to the acetal. You can look at that in your book. Um, but that is protecting group chemistry and synthesis. Two other reactions I need to show you in this chapter. One is amine. So we've talked about formation of amines and amine reactions. So you can take let's take a ketone, do this ketone, and you can react it with a primary amine. So this is a primary amine. Now that's a weak nucleophile as well. I'm not going to go through this reaction mechanism, but you add it with a little bit of acid, and of course we have to protonate first. I will show that. You do the protonation because you've got to activate your electrophile, and now you have the nitrogen adding, right? So your weak nucleophile adds, and here you have NHHCH3, and then you got to deprotonate that to generate your acid again, your acid catalyzed. And this is called a hemi. This is a hemi aminal, okay? It's not an amine, but the next steps are you want your OH to get protonated because you want it to be a good leaving group. You want it to be water. So I will just show this. It's just as easy. This gets protonated. Okay, now you remember before we reformed the carbonyl? Well, now we're going to form a carbon double bond nitrogen. And nitrogen and oxygen are both more electronegative than oxygen. So a lot of times you think of a amine as a lesser reactive carbonyl. So these lone pairs here can go here, and this can be your leaving group. And you form nitrogen double bond. You have a CH3 here and a hydrogen. When nitrogen has 4 bonds, it gets a positive charge. And then we have to deprotonate the amine to nitrogen to form our amine. So we deprotonate that. That makes H3O plus, which is our catalyst, and we form our amine. Okay, so amines are also called a Schiff base. Now, a lot of your amino acids in chemistry and your biochemistry are nitrogens. Okay, so and then your acetals and your hemiacetals and your carbonyls are your carbohydrates. So this is a very important chemistry reaction for biochemistry. It's very important to have your pH around 4.5 for amine formation, and that's because if you have it too acidic, you're going to protonate your nitrogen and it will not be nucleophilic. You do have slides showing this amine formation. What I want to show you is the different amine reactions. So if you take something like cyclohexanone and you react it with ammonia, what does that form? Just lose your water, folks. Okay, so we're going to lose 2 hydrogens here and lose your oxygen. You see how that makes water? And then what are you going to do? You can form a carbon nitrogen double bond. So here, form your carbon nitrogen double bond. All right, and this is an amine. If we take it with like an aniline, so aniline is here. So let's lose 2 hydrogens, minus 2 hydrogens, minus your oxygen. So we've lost water, and you form a carbon-nitrogen double bond. And this has a special phenyl amine. Okay, so you see how we're doing that? Okay, what about this one? What would this product be? So we take benzaldehyde with methylamine. What do we get? Well, lose water. So we're going to lose 2 hydrogens here, lose our oxygen here, form your carbon-nitrogen double bond, CH3. So this is a methylamine. So you can look at other condensations. These are called condensations because we're combining 2 things and we're losing water with other amines. And you can see you form amines. Let's look at an oxime. You can have different functional groups. So oxime would be if you used, this is called hydroxyl amine. So if you took something like this with hydroxylamine, you would get OH, and this is an oxime. If you reacted it with hydrazine, hydrazine is rocket fuel. You don't want to heat this too high in the lab. Okay, so you're losing your 2 hydrogens here and the oxygen, so you're losing water, and this is called a hydrazone. So you can look at those. You should have some reactions in your sapling. We'll be doing carbohydrates soon. Okay, so here I'm going to draw glucose. Glucose has all its OHs in the equatorial position. I want you to see that this functional group here in glucose, this carbon is connected to an OH and an OR. You see that? That is a hemiacetal functional group. Now what happens is you're going to learn that these open up, and that means that this acetal carbon can form an aldehyde. So it can go in equilibrium to an aldehyde. And so when you have glucose, and glucose is an aldehyde, we can draw our Fisher projection. Not sure about the OHs here. 1, 2, 3, 4, 5, 2, 3, 4, 5, 6. Okay, so this is the open chain when the aldehyde, when acetal opens up, and you see that you have an aldehyde here. So you can imagine if you reacted this with, let's say, an amino acid such as glycine, you could form a shift base there. You would lose the water and condensation. So this chapter is your first chapter that you're really getting into more of a biochemistry. Okay, one more reaction is the Vidiq reaction. So now we're going to talk about the Vidiq. A lot of people want to call it the Whittick reaction, but it's German and it's pronounced Vidiq. And you can take an aldehyde or ketone. So let's take something like this, a ketone, and you react it with a phosphorus ylide. So this is called an id. So ylide. And a phosphorus ylide is a ylide means it has a positive and negative charge in the same molecule. So here we have triphenylphosphine, and this is a positive, and this could be something like this, and a hydrogen here, and this is a negative. So the ylide means there's a positive and negative, they're right next to each other, and this is going to be the nucleophile. Now this is a strong nucleophile, folks, so we don't need to add acid like we did in our, so this is a strong nucleophile. So a strong nucleophile, this negative carbon will attack the carbonyl, and this forms a four-membered ring. And that four-membered ring is called a oxaphosphate. Oxaphosphate. And you do need to know this mechanism. So let's form the four-membered ring. So these negative this oxygen, phosphorus loves oxygen. So the phosphorus, and we can just write phenyl, 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 will form a bond with the oxygen here. Okay? And then, but the phosphorus is also connected to the carbon. And that carbon has 1, 2, 3, 1, 2, 3, and it has a hydrogen. And then now we have a new carbon, because you see this bond here, this carbon has now bonded to that carbonyl. And that carbonyl is still bonded to that oxygen. And so then we can add our methyl group there and our ethyl group. So you can see here that this is our oxaphosphate, and it's an intermediate. Okay, now once phosphorus holds on to that oxygen, it's not going to let it go. Okay, so then we're going to get a rearrangement. So the oxygen is going to go to the phosphorus, and the carbon-phosphorus bond is going to break, and it's going to go to the carbon. And this is going to happen in a concerted fashion. Okay, so we know we're going to have stereochemistry here, and that means that if we have this propyl on one side and a hydrogen on one side, it's going to maintain that. We have that methyl and this ethyl. So this is a concerted reaction. That means we have stereochemistry, and you know we're forming what? Alkenes. So this makes alkenes. So we can convert aldehydes and ketones to a new functional group, alkenes, and we know we have cis and trans alkenes. So this was a very powerful way to make alkenes, and it resulted in a Nobel Prize. So let's look at a reaction. So how would you synthesize this compound using a Vidiq reaction? Let's do a little retrosynthesis reaction here. Okay, so we can break this carbon-carbon double bond here, and one of these needs to be a ketone. Doesn't really matter which one or an aldehyde, so we can do that. And then the next one needs to be a carbon phosphorus. So this carbon here needs to be a phosphorus, and then you just add your phenyl, and that makes this a positive, and this is going to be a negative, and there's your nucleophile. Okay, and so the mechanism here is this attacks and makes a, let's do our oxaphosphate. So this carbon here has a hydrogen, it has an oxygen, and then that oxygen now is bonded to the phosphorus. Phosphorus gets the phenols, and it's bonded to the carbon. Carbon has a hydrogen and another carbon. And so there's your oxaphosphate. And then, of course, that collapse. Oxygen goes with the phosphorus. that goes there and gives you the product that you wanted. Okay, actually we do have one more reaction. It's the Wolff-Kitchner mechanism or reaction. So let's do Wolff-Kitchner reduction. This does the same thing, same outcome as the Clemmensen. Do you remember the Clemmensen reduction? The Clemmensen reduction uses zinc, mercury, and HCl, and it was a way when we made like a Friedel's Craft reaction, we were able to do the zinc, mercury, and HCl, and we were able to reduce the carbonyl. Okay, so we can remove the carbonyl. Now the Wolff-Kitchner uses hydrazine and KOH, so it's very basic, and ethylene glycol is your solvent. You have to heat this up to 175 degrees. I've done this reaction. I always get nervous when I heat hydrazine up that high, but you could do this, add that with this ketone, and you would get the same product. So it removes the CO. Okay, so how does it do that? Well, what does this make? It makes a hydrazone, right? So we're going to lose water. Okay, so we lose water. That's our condensation. And then basically you do a nucleophilic attack with a powerful KOH nucleophile, and it can remove the hydrazone. So I'm not going to go through that mechanism. You don't have to draw that mechanism. It is in your slides. Now, why would we care? Why would we want this? And the reason why we'd want this, another way other than the Clemmensen reduction, is let's go back to all right. I would like to make this compound here. Okay, I would like to make this compound here. This is a Williamson ether synthesis. So if we do retro analysis, we'll be like, okay, well, we made an ether here. So we need an alkoxide, sodium alkoxide with maybe iodomethane, and that would make that. How do we make the sodium alkoxide in the presence of a ketone? Well, so let's say we want to protect that ketone. So let's say we want to protect that ketone. So we would like to maybe start with that as your ketone. Okay, so if you need to do a reduction, actually it's probably not the best example. Let's try another example. I was trying to come up with something other than the ketone and the aldehyde, but here's your ketone and here's your aldehyde. Okay, so we want to, let's protect our aldehyde. So now we have our ketone, and then we wanted to add maybe a Grignard to the ketone. So let's add a methyl magnesium bromide to this ketone. And then when you treat this with H3O+, you're going to get your aldehyde back. What if, let's say, so we've seen that. What if we wanted to remove, let's say we wanted to make this. Okay, what if we wanted to make this compound? Okay, so we wanted to actually make that an alkane. Well, we would need to protect our aldehyde. So we could do that with an acetal. So we could take this compound here, and we could add one equivalence of ethylene glycol and some para-toluene sulfonic acid. That would give you that. And then the second thing we could do is we could do a Wolff-Kitchner reduction. So hydrazine, KOH, 175 degrees, and this is also an ethylene glycol. All right. And then the third thing we'd have to do is H3O plus to release. So if we did those 3 steps, we could make this compound. Now, could we have used the Wolff-Kitchner, or could we have used the Clemmensen? Not if we wanted to keep this on, because yes, the Clemmensen could reduce this carbonyl to the CH2 here, but it would also hydrolyze the acetal. So that's why it's nice to have a basic way to reduce this carbonyl other than just an acidic way, because the acetal will not be stable in acidic conditions.